So I was updating the Chem1B website, and I added the link to the videos that Rex has been taping. Rex is doing an excellent job with the video, so I encourage you, if you want to review the lectures, to watch those videos. Now I'm going to ask Rex, is there some way for you to delete my image from those videos? Because I spent about a minute watching one of them just to see how they look, and I really just cannot stand watching myself. So
I can try, but it'll take some editing time.
You probably don't want to do that.
You want me to put like a chicken head on it?
Yeah, it might be a good idea.
I can do that.
So maybe what I'll do is I'll try to spend as much time as I can out of the picture, and then have you guys come up and you guys can watch yourself on YouTube. Instead of watching. Okay, so on Tuesday's class, we are using colligative properties to determine the molar mass of the substance. And we found that this white substance that this forensic chemist was studying was not cocaine. Okay, so before we move on, are there any questions on problem 13.84? And again, that was this one about the forensic chemist had the white solid dissolved 0.5 grams of the white solid and 8 grams of benzene, found a new freezing point of that resulting solution, and concluded that that compound is not cocaine. Is there any questions on that one? Okay, now let's go to part B. Now, note that in this problem, this scientist used freezing point depression as opposed to boiling point elevation. So why do you think freezing point depression is used to determine molar mass rather than boiling point elevation?
Would it be because the substance is a solid?
That's true, but remember that according to the colligative properties, that property depends on the amount of solute present in the solvent. So for example, if you dissolve that white solid in benzene, the freezing point would be depressed, but the boiling point would also be elevated. Actually, let's take a look. If you have your textbook on page 13, page 450, table 13.2. Okay, so let's take a look at this table. Okay, so on this table, it lists various solvents. So let me list the solvent, the KF, and the KB. Okay, so here we have. And tell me if you see any trends in this table. Okay, so Kb is the boiling point elevation constant, Kf is the freezing point depression constant. So do you see any trends looking at the numbers in this table?
Freezing point.
Yeah. So note that, like Jeff's noticed, the Kf value is higher than the Kb value for all these solvents. So what does that tell you about the elevation and boiling point compared to the depression and freezing point if you use the same concentration solution?
It's more noticeable change.
Yeah, so according to the equation, so we have delta Tf equals I times Kf times m, or delta Tb equals I times Kb times m. So let's say we use the same concentration of the solution. The freezing point is going to have, like Miguel says, is going to be bigger. In other words, the depression of the freezing point will be bigger than the elevation. Now, when you do an experiment, does that make a difference? Okay, so let's say, let's put some numbers in. So let's say the molality is equal to 1 molal, and let's say that the I value equals 1. That means that if we plug these numbers in, delta Tf is going to equal, let's say we're using water. Let's say the delta Tf then is going to be, let's see, 1.86 degrees, whereas delta Tb is going to be 0.52. So note that from the same concentration solution, you get a bigger change in freezing point than in boiling point. So how does this affect an experiment? Okay, so remember way back in Chem 1A, during the first week in the semester, we looked at scientific measurement. And when you're making a measurement, remember that every measurement that you make has uncertainty associated with it. So, when you, let's say that the uncertainty in your temperature measurement was plus or minus 0.1 degrees. Okay, so let me write that here. So if your uncertainty in temperature is plus or minus 0.1 degrees, and you measured the freezing point to be 1.86 degrees, okay, so if the freezing point is 1.86 degrees, that's plus or minus 0.1 degree versus the boiling point, which is 0.52 degrees plus or minus 0.1 degrees. Now, which number is going to have the larger error? Why the boiling point? Yeah, because note that what you can do is you can take 0.1 divided by 0.52. That gives you like a some percentage value for the error, versus 0.1 divided by 1.86. Okay, so really that's the reason for using freezing point depression rather than boiling point elevation when you're doing these kinds of measurements. Okay, because generally speaking, the error will be smaller. Okay, let's go into question C. Osmotic pressure can also be used to determine the molar mass of a substance. So this is problem 13.87 on page 463. And that problem states, a protein has been isolated as a salt with the formula Na20P. This notation means that there's 20 sodium ions associated with a negatively charged protein. The osmotic pressure of a 10 ml solution containing 0.225 grams of protein is 0.257 atmospheres at 25 degrees. Calculate the molar mass of the protein from these data, and then what is the actual molar mass of the protein? Okay, so let's write down these maybe here. Okay, so this is 13.87. Yeah, do you guys have your textbooks? I don't have to write this down. I only see a handful of you.
I have enough.
So you guys need to bring your textbooks. Okay, so you have a protein. And the formula is Na40P. And this is according to this information. You have a 10 ml solution. And let's see, it contains 0.225 grams of protein. And let's see, the pressure is 0.257 atmospheres. And then last piece of information, the temperature is 25 degrees. So based on this information, we can calculate the osmotic pressure. Actually, no, we can calculate the molar mass of this protein. Now, we haven't used this formula in class yet. The equation for osmotic pressure is this one. Okay, so osmotic pressure is given this Greek symbol pi, and that's equal to I times M times RT. Okay, so I is the same thing which as in freezing point depression, 1 point elevation, that's that Van Hoff factor. M is the molarity of the solution. Okay, so M is the molarity, which is the concentration unit. Note that the other formulas use molality. This one uses molarity. Okay, so this is moles of solute per liter of solution.